Okay, Adam, are you ready?
Sure.
All right, so good day, everyone. Our speaker today is Adam Rennie from the University of Wollongong, Australia. And Adam is going to tell us about the constructive Kasparov product. Adam, please.
Thanks, Ruspe, and thanks for the invite to be here, wherever here is. Hope you're all enjoying it. So this is just going to be a pretty quick overview and skipping details. I really had no idea who I'd be talking to or what people would know, so I'm just going to tell you what me and a bunch of people I know have done. I probably won't mention everyone here explicitly, but at least some of them. And now I have a problem with my screen sharing to... there we go. All right, so the basic idea is that we use geometry to access topology, and we use topology to tell us about what we can do geometrically. So here I mentioned a few examples. Closed differential forms can give you cohomology classes. When you play Chern-Weil theory, you're actually getting your Durham classes directly from the curvature of vector bundles, and in the Atiyah-Singer local index formula, you're using both those things to compute the pairing of K-theory and K-homology. So the idea of this talk is about geometric realizations of Kasparov modules, which represent classes in KK, which is topological, of course. So the idea of trying to find more geometric representatives is so, well, it can help us guide us in the non-commutative world, for one thing, but usually they're a bit closer to calculus and give us more computational tools. And the computability is actually the thing that's most helpful in this setting. So in the more abstract setting, one would try to use positive splittings of exact sequences to do Kasparov products and so on. But very often an exact sequence is not, you don't get it with a positive splitting, so you can try and do something else. But I'll say something more about that later. So, all right, at the risk of saying something I've said very many times, is I'm going to tell you about what Kasparov modules are. I'm going to keep it as simple as possible. So no group actions. Everything is going to be complex, not real or real. And but I do want to just keep the Z2 graded so everything's applicable to both the even and odd case, which I'll say very little about. So my C-star algebras will have an even part, A0, and an odd part, A1. And this just tells you things like even times odd is odd and so on. Okay, so if I've got two, I'll also take them separable just to avoid any issues. So I've got two separable C-star algebras, A and B, and then a Kasparov module for them, which I'll write in this way. Several things. First of all, it's a right Hilbert B module. So this is a Banach space with a right B action and a B valued inner product, which is suitably sesquilinear. The best way to think about this is if B is the complex numbers, this is a Hilbert space. You have homomorphism, which allows A to act on this module. So this end here is the B linear operators on X, which have an adjoint for your inner product. And not all B linear operators do. But, because I want X to be Z2 graded, so I'm splitting it up as a direct sum of 2 bits as well. Sorry, something's gone wrong. What happened there? My computer is behaving as if it's not plugged in, but it is. Okay, so there's a direct sum x0 plus x1. Essentially, this Z2 graded homomorphism. An odd element in A is sent to an operator that swaps the two pieces. An even element preserves them. And here, the last ingredient is an odd operator, so one that swaps x0 and x1. And this operator we want to almost commute with the action of A, almost be self-adjoint, and almost be square the identity. So that's these three conditions, where almost means that the error is always compact. And I won't tell you what the compact endomorphisms are in general. We'll talk about it in examples from time to time. Okay, so that's the bounded ones, and that's what you build KK theory out of. So the more geometric version is an unbounded Kasparov module. It starts off exactly the same. We have right module over B, a left action of A. And what we're going to do is replace the operator F, which, well, roughly this says it's an order 0 pseudodifferential operator. This says that it's elliptic. It's not entirely obvious, but that's what they say. What I'm going to do is get rid of the middle condition by taking my operator to be self-adjoint on the nose, not just approximately. That's for technical reasons. And I want it to act like a first-order differential operator. So typically it will be unbounded. It doesn't have to be, but it usually is. There's this regular, which is an extra technical condition you need for C-star module operators. And again, it's odd. And so I have two conditions to emulate. And the first one is basically the collection of algebra elements in A which preserve the domain and have bounded graded commutator should be dense in A. And I'll write curly A for those guys. And A times basically the resolvent of D is a compact endomorphism for all A. So this one says first order, this one says elliptic. And I'll just say this for now. If B is the complex number, so the X is a Hilbert space, this is also called a spectral triple. Okay, so first thing at the top, KK groups are built from homotopy classes of bounded Kasparov modules. I'm not going to go into what the exact relations are. We don't need it today. In 83, Barge and Yule showed that whenever you have one of these unbounded modules, you get a bounded one by using the functional calculus to build this operator here. They also showed that every class in KK can be represented using an unbounded Kasparov module in this way. And their motivation was to be able to compute sort of, if you like, the easy version of the Kasparov product. It's not entirely easy. It's called the external product. So you can see it's a map from two abelian groups to this abelian group. It should be bilinear. It's a very nice product. But the main thing is you can capture this immediately using the unbounded formalism. If I have a class in here, I represent it with an unbounded guy. Same for the second one. And then a representative for the class over here you get from the external product is this very simple formula. It's tensor products of algebras, tensor products of modules, and then you have this construction for the operator. So let me give you a couple of examples that are sort of reasonably geometric. I'm going to start with a vector bundle on a nice paracompact Hausdorff space, so I can choose a Hermitian inner product. And then the sections vanishing at infinity of that bundle is a right module over C0M. If M happens to be compact, and E is finite rank, and I think all my vector bundles will be finite rank, then the endomorphisms coincide with the compact endomorphisms. That's what this little zero means. And they just happen to be the sections of the usual vector bundle endomorphisms. And in this case, the identity operator on X is compact, and this little triple here is a Kasparov module in KK. I don't know if I can pull this off. C, B. There you go. So that's a K-theory class. And without any further information, all the Z2 gradings are trivial, so everything is even. If M is not compact, but you still have a finite rank vector bundle, then the endomorphisms are the bounded sections of the usual endomorphisms, and the compacts are the sections vanishing at infinity. And in this case, the identity operator is not a compact endomorphism. So this isn't a Kasparov module of either sort. You can put an operator here instead of 0 to make a Kasparov module, but I'm going to do something else. So I'm going to specialize to the case that I've got the complex spinor bundle on a compact Riemannian, oh, sorry, I don't want compact here, sorry, on a Riemannian spin C manifold. Then you can represent the sections of the Clifford algebra constructed from the cotangent bundle as endomorphisms of S. And so you get a Kasparov module here. Okay, and this one is graded when M is even dimensional, and this example is also a Morita equivalence bimodule. So Kasparov products, which I'll talk about soon, with these sort of classes are actually isomorphisms. Okay, so different things you can do to construct them, these classes. Here's a different sort of thing. If M is again a spin C manifold, then you can use the Clifford algebra to build a different sort of class. So if you take a local coordinate basis of the cotangent bundle, what we can do is write gamma mu for the Clifford action of dx mu on the spinor bundle. You can lift the Levi-Civita connection to a connection on S, and this is your Dirac operator. It's elliptic, it's first order, and this data here is well known to give you a spectral triple, so unbounded Kasparov module. Okay, so that's a few different sorts of classes. All right, how does the Kasparov product work? What is it? It's slightly more general than this, but doing this case is adequate. So the internal product is, again, a bilinear map from this pair of abelian groups, which is functorial and associative. It's extremely robust. It's a little bit groupoidy in that you've got to have the same algebra in the middle to compose two things, right? Now, essentially, given classes here, you'll see in a minute there's an obvious way to construct a module for out of the two classes, or representatives of them, but the trick is building an operator that makes it work. And Kasparov showed that any two choices of such an operator give you homotopic representatives. So you do get a well-defined product, but on these homotopy classes only. In 84, in the longitudinal index theorem for foliations, there's Skandalis introduced a sort of a guess and check method for determining the product. The idea is you often know what the product ought to be for geometric or topological reasons, and you want a clean way to be able to prove that that is in fact the answer. And so they gave criteria there. What we're trying to do is actually figure out when you can write down a formula in terms of
Can I interrupt you a little? I mean, what we did with Skandalis, we defined the notion of a connection, which is of course central in this topic.
Yeah, we're going to play a similar game.
Yeah, exactly. So, I mean, but the advantage was in what we were doing is that, connections always exist and they give you the product in all cases. So, I mean, this is quite different from the unbounded case.
Right, yes, but you still very often, they do exist in the unbounded case, but in a different way.
Sure, okay.
Sure.
We'll come back to that, but I just...
Sure. Okay, so so what we want to try and do is just take two unbounded guys as input and produce an unbounded guy as output, which represents the product. Ideally, you want to carry along as much geometric or dynamical or physical information as possible, but since the product's only topological, as Elaine was just saying, something has to give. All right, so for the external product, we had this formula from Baj and Yule at the top. So these tensor products are over the complex scalars, whereas for the internal product, we need this B data to disappear. So what we do, given these two classes here, what we want to do is form the internal tensor product or balanced tensor product, which is the usual. These are Z2 graded tensor products, but I'm hiding some minus signs. So you take this usual tensor product and you divide out by this submodule, which forces the B linearity of the tensor product.
Yeah, I think Belisa has a question.
Yeah.
Yes, I thought that in the first line, in the contribution of the Dirac operator, when you add them up, the two parts should anti-commute instead of commuting.
Where am I? Oh, here.
Yes, in the Kasparov product.
Yeah, that's hidden in the Z2 graded tensor product, Sean.
Okay.
Yeah. So there are minus signs when you jump over a tensor product.
Okay, thank you.
All right. Okay, so given the formula at the top here, the first thing you might want to try is this as your formula. Now, for S tensor 1, there's no problem, but the operator 1 tensor T is not well defined on the balanced tensor product unless T commutes with B. So that's just not going to work. So really, the starting point always includes this sort of module data. There's nowhere else to go, seemingly, not any reasonable choices. And then you've got to guess your operator, or maybe you're happy to go with S tensor 1 and just need to guess what you add to it to capture the information from T. If you actually come up with a guess, how will you know if it works? Well, in 97, Kucherovsky translated the Conon-Skandalis conditions into sufficient conditions on an unbounded Kasparov module defined on that product module to represent the product of these two. So we do have conditions where we can check if we have the correct answer. So here's some of our examples back. I have a compact spin manifold and I have a complex bundle on M, and we can talk about this product here because we have both classes. And the class should lie in KK of the complex numbers twice. That should be and that's the integers. So I don't know who originally wrote this down. It's an old geometric construction of how to write down an operator on the tensor product of these bundles. I'll describe what this is in the next page. But it does rely on an additional piece of data, which is a connection in the classical diff-geom sense. So how do you define one tensor nabla D on a simple tensor? Well, you write down the one tensor D that you would like to work, but doesn't, and then you need a correction term. The way the correction term works is you write your connection in local coordinates like this, and then you let the dx mu act on the spinor bundle by gamma mu, and that's how you get nabla ES. So using the basic rule for connections, you can check that your one tensor D, or one tensor nabla D, is well defined on this balanced tensor product, and the balanced tensor product is the sections of the tensor product of the vector bundles. And I can happily put an L2 there if I want as well. That makes no difference. All right, so what we want to emulate is connections on modules of sections in the general case. So you got to have some notion of C1 elements of modules and algebras, but the unbounded Kasparov modules come with this because you have your curly A in the algebra, for instance, and you have the domain of D contained in the module, which is also something like a C1 kind of condition. Not exactly. Now, I'm going to skip the analysis because it gets quite hairy, but the way to make these conditions work more generally is using operator spaces and the Högerup tensor product to handle the analysis. With that in place, then the algebra is more or less unchanged when it all works. So what I'm going to do is tell you the sort of computational tools we use to play with these connections and where they come from, or how we build them in practice. So if I've got a right module X and I take so separable, countably generated, if you've got a countable set in there so that for every vector Y you can write it in this form, then we call the XJs a frame. In the signal analysis language, that would be a tight normalized frame. I'll just call it a frame. Okay, so this is a computational tool. A Kasparov stabilization map is an adjointable isometry into this gadget here. This is the standard Hilbert module of sequences. So it basically looks like little L2 tensor A, completed so that these sequences converge in the algebra. And that tells you what the inner product is too. Since V star is a projection, X looks like, it's not quite a projective module in the categorical sense because HA is not really free. It's not a free direct sum. There's some convergence condition in there, but it's good to think of it that way. These two notions are equivalent. And since Kasparov proved stabilizations always exist, frames always exist. So if you're given a stabilization map, then what you can do is go over to the standard Hilbert module. I put a twiddle here to unitize if I need to, just so I can put ones in every slot and have the standard basis. If I pull them back, that's a frame. And if I'm given a frame, then I can define my stabilization as this column vector here. Okay, so frames and stabilizations go together, and we're going to use them to build connections in a minute. If I have a Kasparov module, I can define the one forms associated to it. So we're thinking of these like differential one forms. And these are a set of operators on the module Y. Then once you have a set of a bimodule of one forms, you can go ahead and define a connection. Now, I'm going for a curly X, so this is meant to be nicer than a C-star module, but we don't know what it is yet. So a connection on here is a complex linear map that is almost alinear, or it's a derivation, whichever way you want to think about it. So it satisfies this rule. And if I'm given a frame, I can define a connection, at least algebraically, by this formula. And you can check that that's a connection in very close to the differential geometry sense. So I've started raising problems. What's a frame for this curly X? So certainly you've got to have these inner products lying in curly A so that you can take commutators with D. You've got to have some sort of convergence so that the frame relation makes sense, and you must have a topology on this product so that convergence makes sense in this expression as well. And this is where you're really using a lot of Hogarth tensor product. But I'll spare you. Okay, so now we're given a connection and given these two modules, Kasparov modules, and this is the formula we would like to write down. All right, so does it work? Well, there's several things that you need to check. Well, you need this product here to be self-adjoint, but it's pretty hard to address that if you don't know that this guy is self-adjoint. And so you ask, first of all, is that self-adjoint? Then you ask if this sum is self-adjoint. And if they both are, then you're lucky because this relatively compact condition is satisfied automatically. But you still may fail because these commutators may not be bounded, so you don't actually have a Kasparov module. So this first point here is where you really need the Hogarth tensor product. So this is a very loose statement of what's known, because to say anything more precise would be really tedious. So if I've got two Kasparov modules unbounded, and I've got a nice smooth submodule of some sort, I'll say something about that in a minute, then there is a connection so that this is self-adjoint. And if on a suitable domain, these are graded, so anti-commutators can be bounded by, I guess the right thing to call this is the combined graph norm, then the sum is self-adjoint. And finally, you just need to check this commutator, and there's nothing you can do about that I know of. You just have to check that that works. If everything works, then this does indeed represent the Kasparov product. What would be a nice module? Well, if I write X as a projective submodule of the standard module, then you want either to be a direct sum of projections in matrix algebras, so a sum of finite projective modules, or you want the projection to have bounded commutators with T, and you've got to say that appropriately in this balanced tensor product. There's lots of examples where the projection does not have bounded commutators. So old work of Brain and Mesland and Van Silicom looked at Hopf vibrations and theta deformations of them, where these PJs are the projections defining tensor powers of the Hopf line bundle. And as the curvature of those bundles grows, so too does the norm of the commutator. So you definitely do have to deal with projections that have unbounded norm of commutator. And that's just a thing, but you can do it. All right, so this covers a lot of examples, not everything in the world, and certainly everything I mentioned can fail. So for instance, this last condition about the commutator, if you take the spectral triple for the Podlesh sphere that's due to Dubrovsky and Sitars, and you take the natural Kasparov module that you get from the circle action on SUQ2, and you put these two, which has fixed point, the Podlesh sphere algebra, you can bang those things together and everything works except this guy, and that fails, and it fails really badly. So anything can happen. All right, so this theorem in various forms is due to Mesland in his thesis, and it took a while to get published, and Carl Lesch, and I wrote a paper with Bram Mesland as well. That sort of optimal condition on the self-adjointness of the sum is due to Mesland and Lesch in 2018. And Carl van Silicom were using, and Van den Dungen were doing things with weakening the conditions on the inputs so that they needed only be symmetric operators and not self-adjoint. So there's various versions of this around with slightly different hypotheses, but this is the basic idea. The proof in the paper that I wrote with Bram actually gives an alternative proof of the existence of the Kasparov product, because we can show that every composable pair of K classes can be represented by unbounded modules for which the formula does work. Now, that is, of course, not constructive. It's a very non-constructive thing to build those classes. I still think the strength of the constructive product rests on the fact that a lot of naturally occurring classes are already unbounded or geometric. Just to show you how these things work in practice, if you've got your vector bundle and you take an open cover of trivializations and local orthonormal bases and a partition of unity, then you can build a frame in this way. The projection that you get out of that has entries that look like this. So that's if you take the Dirac spectral triple to define your one forms, then this is what the connection looks like. So this bit looks basically like the classical situation. You've got derivatives in all directions locally, and this term is sort of a slightly global correction that comes from your partition of unity, which pastes it all together. And of course, this is the operator you get out of 1 tensor nabla D. All right. So this is not much of a theorem, really. This is pretty easy to prove once you have without this machinery. I'm just showing you that it can reproduce something else. If you've got a bundle on your compact even dimensional manifold and a Dirac type operator on S over M, then this product here does represent the product of the two things you started with. And of course, now you have to take the index of the lower left corner of this 2 by 2 matrix operator to realize exactly what the integer is. And at this point, probably the easiest thing to do is use the local index formula of Kohn-Moscovici, which computes the answer in terms of D and, well, the projection associated to E. And so this is in itself a constructive formula for the local index, for the Kasparov product in a particular case. And yeah, it's a whole other story, which we should probably not get stuck in. But there's a connection, of course, back to the original Atiyah-Singer local index formula due to Bloch and Fox, who used Getzler's rescaling to derive the original Atiyah-Singer formula, and that was refined by Ponge a bit later. Okay, so my plan now, just having told you what can happen if everything works out, is show you that in some cases it does work out. And what you need to do to use it in a couple of different examples. So I want to talk about the bulk edge correspondence for topological insulators, but I'm just going to really talk about the Hall effect because this is a whole other subject on its own. So I start with an effectively 2D piece of conductor, put a magnetic field perpendicular to it, I put a voltage across so I get a current this way, and then the right-hand rule tells me that you get this drift current or transverse current, or Hall current it's called, in the transverse direction. The conductance in that direction varies proportionally to 1 on the size of the magnetic field. And so that's a linear relation. But once you go near 0 temperature, von Klitzing showed that it was actually quantized in units of E squared on H. And in this sort of region here, you can vary the magnetic field and other parameters of the material, and the index doesn't I'm giving it all away, aren't I? The conductance doesn't change. Jean and Alain have shown that there is a Fredholm module, and it has an unbounded representative, which is an unbounded Kasparov module, which pairs with the Fermi projection of the Hamiltonian of this system to give the conductance in those units of E squared on H. So it's known that you can explain what's going on with the quantization here using index theory. Now, somewhat later, Kellendonk, Schultz-Valdez, and Serge Richard gave us an exact sequence. So I'm going to do this in the simplest possible case. Here's my 2D material, and I'm just going to model it by integers squared, which is pretty lazy, but let's do that. And U is then going to be the bilateral shift in one direction. V is the bilateral shift in the other direction. Except they don't commute. Because of the magnetic field, as you move around a square, you're going to pick up a phase factor. And so this guy here is actually a rotation algebra. Here, I'm going to introduce an edge. So we're going to look at what happens to our system in the neighborhood of one of the edges of our material. So now U is still a bilateral shift, but V is an isometry. So U is unitary, V is an isometry. Over here, I'm thinking about just the edge, where I have U being a unitary. And these compacts, we think about modeling the transverse direction, but these are things that decay quickly away from the edge. That's why they're compact. And ignoring disorder, the Hamiltonian is this sum of shifts. So moving away from that picture, that's what our exact sequence looks like. Now, I briefly mentioned this, and it's another long story. When you have a short exact sequence, you actually get an element in KK, and there's a little 1 there. What the 1 means is I could just talk about KK and tensor on a Clifford algebra here if I want to, or something like that, but we're not going to worry about it today. The question is, how do you represent that extension class as an unbounded Kasparov module? And this is a bit of an art, but because the Kasparov product with such extension classes give you boundary maps in K-homology and K-theory, they can be very useful for building new classes. For instance, we know a lot about K-homology of the circle, and by taking a product with this extension class, we can build K-homology elements for the rotation algebra. So representing X by an unbounded class is something of an essential step in a lot of applications. So in this case, it's pretty easy. It turns out that the rotation algebra acts very naturally on here. So one of my generating unitaries acts as the generator in C of S1. The other one acts as a slightly phase twisted shift on L2 of the integers there. This is the position operator in the transverse direction. And if you think about the Hardy projection of this guy, so the projection onto the non-negative spectrum, you can compress everything in the rotation algebra by that projection, and you pick up the middle algebra in our exact sequence. So by coming up with this representative, we are also coming up with the positive splitting of our exact sequence. They're not entirely equivalent bits of information, but it's not far off. Of course, the position operators are physically relevant, and in this setting, they also give commuting derivations on the rotation algebra. And we can build a position operator for the bulk in this sort of Dirac way here. And this is about the simplest version of the bulk edge correspondence due to Chris Bourne, Alan Carey, and myself. It was just after the Hausdorff meeting, I guess 2014, 15. Okay, so this here is the minus the Kasparov module that pairs with the Fermi projection to give you the conductance. Now, this has been known for a long time. And so this bit here is due to Belisard. Over here, what we have is the product of the fundamental class for the circle. So you could put any other class for the circle here if you want, and our extension class. Because I can prove that this guy here is the product of X and this XE guy, I can now use associativity of the Kasparov product to find a class V, which is going to be a K-theory class, an odd K-theory class for the circle. So this is a unitary, and it's telling you how to jump along the edge. And it was proved, I think, by Schultz-Baldes and Prodan in their book, at least. The right-hand side here is 1 on the electronic charge times the current density on the boundary. So what we have here is this sort of stable topological quantity for the bulk theory, and it's related directly to a current around the boundary. And that's really what the bulk edge correspondence is all about. Okay, so there's lots of different generalizations. Yep.
Just a second. I am a little bit sort of confused here, because what I remember well, you know, in the early 80s, I mean, with the work of Belisard and so on, was that there was a key of this time of the bound of the quantized calculus. And the reason was the following. And the reason was the following. It was that if you want, you can have functions on the 2 torus or on non-commutative torus. I mean, there is no difference there, which are such that their commutator with the canonical F is of the correct class, and these functions are not continuous, so they don't belong to the sister algebra. So
yes,
this was,
but that's an effect of the localization.
It was an effect of the localization. So this was absolutely
yes, but here he has no disorder.
Yeah, when you add disorder, those sort of effects come in.
I understand, but what I am saying there is that if you want, there was a feature which was essentially only detected by the quantized calculus, by the bounded commutator with a bounded, and I don't see how this could reflect itself in the unbounded situation.
Yeah,
I'm not sure. I mean, I'm just asking the question.
Yeah.
And you see, I mean, so for instance, this is also what happens when you take even S1, where you can have functions with commutator with the Hilbert transform as some Schatten class, as you know very well, where you have the link with the Hausdorff dimension and so on. So, I mean, that type of estimate, I don't know how it is related to the unbounded situation. I have no idea, actually.
I don't think it's hugely important, except that when you add the disorder in this class, the extension, it appears in the extension class, you end up having to use the integration over that space, and you do use the cocycle. We use the local index formula to compute it. And you're equating 2 things. One is the pairing, and it's in K-theory, and you apply.
No, this I understand.
And on the other side, you have a cocycle which extends to a bigger algebra. So it's using that extension to go to the bigger algebra, and on the other hand, knowing it's already an integer to control the quantization.
I understand. Okay.
Yeah. So no, there's some more steps there.
But nevertheless, I don't think there's been a successful result concerning the absence, the case of disorder with absence of gap for this bulk edge correspondence. For the bulk, we understand what to do, but for the edge, I don't remember seeing anything that has been done.
Yeah, I'm always a bit wary about the disorder on the edge, because one of the artifacts of this approach is that the disorder space for the edge is the same as the disorder space for the bulk, which seems a bit strange to me.
Nevertheless, we know that these edge current persist. It's protected. We know from other argument in physics. So it would be nice if we get an argument prove that in the context of K-theory.
Yeah, I'm sorry, I haven't got that for you today.
Okay, thank you.
Alrighty. Okay, so there is a lot you can do here. So Kitaev gave us a whole periodic table of these things. So different dimensions, different combinations of symmetries. People have since worked with aperiodic lattices, so Chris Bourne and Graham Meslin. There's continuum models. So I used a lattice model, but you can do a continuum model. Chris Bourne and I looked at that. And of course, you have to add disorder. So there's a lot more bells and whistles you can add to this. Most of these generalizations, because time reversal and charge conjugation are both complex antilinear, you end up having to use real KK theory, but our results on the Kasparov product are basically unaffected by that. So you can use the results in the real case as well. And the versions of the bulk edge that we have in the complex case go through in the same way. You find a geometric model for the extension class. You can take the product explicitly, and then you're using associativity of the Kasparov product to relate the bulk to the edge. All right, that's pretty much all I wanted to say about that, because otherwise we'll be here all night. So the last one I want to talk about is very different. So that was, I guess, a physical example, but felt quite geometric. This one is more mathematical, and it's a dynamical system, and the algebra is extremely non-commutative, and it's got a different flavor altogether. So one can do dynamics in lots of ways. You could use groupoids or whatever. I'm going to look at the Kunz-Pimsner approach, due originally to Pimsner in the middle of the 90s. And it starts with, again, a right Hilbert module. But this time, instead of another algebra, we have the same algebra acting on the left. So that's a self-correspondence. So here's two of these things which are worth looking at. If you've got an automorphism of your algebra, you can define this really boring inner product. So you can turn A into a module over itself, and then define the left action by using the automorphism. If you have a finite directed graph, so these are vertices, directed edges, range map, source map for the edges, we can let the algebra be functions on the vertices and the module be functions on the edges, and given A and B in my algebra and X in my module and a G is an edge, I was running out of letters clearly, you can define the action this way. So X is just evaluated on the edge, A is evaluated on the range of G, and B is evaluated on the source of G. The inner product sums this product over all edges whose source is that vertex. Okay, so that's how you define a function on vertices out of two edges, or functions on edges. Okay, so that's two quite different sorts of module. Given the self-correspondence, and for simplicity, I'm going to take the left action to be injective and act by compact endomorphisms. Then you can build this Fock module. So this is taking a direct sum of all possible internal tensor powers. The zeroth one here is a copy of A with trivial left action and trivial right action. Okay, so that's what the zeroth power means. Once you've built this module, you can take any element of your original module X and create and define a creation operator, which just puts an X on the front of any tensor. This guy's adjointable, and we define the Toeplitz-Pimsner algebra to be the C-star algebra generated by the left action of A and all of these creation operators and their adjoints. You can show that Toeplitz-Pimsner algebra contains the compacts on the Fock module, and so we get an exact sequence where the quotient is what we're after. That's the Kunz-Pimsner algebra. So once again, we have an extension, and of course, it defines this algebra, and that's what we had last time as well. And so we would like to represent this extension as a KK class, and we'd like to do it nicely. Just as examples, if you start with an automorphism correspondence, what you get is the cross product. If you start with that finite graph, the Kunz-Pimsner algebra is the C-star algebra of the graph. So very well studied. Okay, so this is what I was saying about the extension class. Again, in the Pimsner-Wojciechowski sequence, these boundary maps are given by Kasparov products with that extension class. So we would like to be able to represent it nicely. To get a nice representative, you kind of need to start with a nice module. Or at least that's what we know how to do so far. So if you have a self-correspondence, it's going to be a bi-Hilbertian bimodule. So as far as I know, this was introduced by Watatani and co-workers. And this is when there's also a left inner product, so that the two norms you get are equivalent, and then the right action needs to be adjointable for that left inner product. And this is not as uncommon as it sounds. So here in the automorphism case, you can define the left inner product very easily using the automorphism. And for the graph case, instead of summing over the source, you sum over the range. And that's all there is. This first example is a Morita equivalence bimodule, but the second one is usually not. For most graphs, it is not. So even though you have two inner products, you're not talking about having that Morita equivalence compatibility. And there's some slight lies here just to avoid technicalities, but the module has finite index if for any frame for the right module structure, when you add up the frame in the left inner products, it converges in A. Quite amazingly, the resulting element is central, invertible, and positive with the assumptions that I've got. Okay, so we're going to start with a bi-Hilbertian bimodule of finite index. And there's going to be two side conditions. I'm not going to tell you what they are because they're rather technical and we don't know any examples that don't satisfy them. So it's kind of uninteresting in some sense. One of these side conditions guarantees that you have an expectation from the Toeplitz algebra to the coefficient algebra A, and it vanishes on the compacts. So you can define an inner product using this expectation. I'll use a pen. So you can do, so if I've got two elements of my Toeplitz algebra, what I'm going to do is define this to be phi of T star S. Right, okay. So that gives me an inner product. It's got lots of zero vectors because it vanishes on the compacts. So when you quotient out all those zero vectors and complete, you end up with a right A module, xi, with a left action of the Kunz-Pimsner algebra. Inside that module, there's a complemented submodule F, which is isometrically isomorphic to the original Fock module. And the projection onto that guy defines a bounded Kasparov module. And it represents the extension class. So we can actually identify the extension class as a bounded Kasparov module. To do better, you need the second side condition. And again, I'm just not going to go into it right now. And the second side condition tells you that this module breaks up as a direct sum of finite projective modules. And you can find real numbers so that adding up those numbers times the projections onto the submodules defines an unbounded Kasparov module. So you have to have bounded commutators with OX, and this guy needs to have compact resolvent. And that works. So the bounded version was proved by Dave Robertson, Aidan Sims, and myself, and the unbounded version was proved by Bram Mesland, Magnus Goffeng, and myself. And the unbounded version really built on work of Goffeng and Mesland studying Kunz-Krieger algebras. So in the Kunz-Krieger setting, they looked at the groupoid picture and the Diaconou-Renaud groupoids. And these are built from shift-tail equivalents. And essentially, there's two parts to the shift-tail equivalence. That there's how far apart two things are and how far along the sequence you have to go before they become a constant distance apart. Usually, so one part of that equivalence relation generates a circle action on the algebras, and the other part has mostly been neglected. But actually, it's critical for building this spectral triples and Kasparov modules that I'm describing here. And it's called the depth core operator. Roughly speaking, if you're looking in the fixed point algebra, which is a direct limit of matrix algebras in the Kunz-Krieger case, what the depth core operator tells you is how far into that direct limit does your algebra element first appear? What's the least distance into the direct limit you have to go, roughly? So this is much more dynamical. It's got less to do with geometry and more to do with the dynamics and the equivalence relations defining the dynamics. But having built that class, you can now construct explicit dynamic representatives for k-homology classes of cross products by starting with that automorphism situation. Kunz-Krieger, the case of Kunz algebras was done explicitly by Bram and Magnus again. You can relate the whole Kunz-Pimsner thing back to mapping cones, as I did with Francesco Ricci. And you can also show that Poincare duality, which was originally studied for Kunz-Krieger algebras by Kemminker and Putnam, can be extended to this Kunz-Pimsner setting. So that was with Dave Robertson and Aidan Sims again, pretty much in the context I've talked about. There's also been much more done on Smale spaces in this context by Putnam and Whittaker, Dealey, Goffeng and Mesland again. So there's lots of things with a very different flavor in the dynamical direction. There's lots of other things going on. Walter, whose smiling face I can see right there, started using Kasparov products to do gauge theory some time ago. I can't remember how long ago now. And there's been steady progress around that. So I mentioned the work of these guys on Hopf vibrations, but more recently there's work by Kacic and Mesland who actually use the unbounded Kasparov product as a tool to identify gauge groups and work with non-commutative principal bundles. I guess my takeaway message today is that though it doesn't always work and it doesn't always do what you want, when it does, the constructive Kasparov product gives you a calculus for combining and factorizing these topological invariants. And it gives you some guidance on how to build geometric objects in highly non-commutative cases. And I don't know, I put in a lot of references and it's still not enough, but thanks for your time.
All right, thank you very much, Adam, for a very nice talk. If there are questions or comments, just please go ahead and ask Adam.
Yes, I have some kind of a general comments, because on this sort of general trajectory. So I think the original idea. I mean, so after the work of what Atiyah did on abstract elliptic operators in his old paper. Okay, then things were they had been worked out by the extension theory of Brown-Douglas-Fillmore. Yep. And then, okay, Kasparov obtained like the perfect bivariant theory. I mean, what he introduced that was new, if you want, with respect to the previous approaches was the fact that you have a bivariant theory where you have a cup product where you can combine. And of course, this is great because, I mean, it allows to sort of incorporate very, very different situations.
Yeah.
Now, what I noticed at the beginning of the 80s was that by, just in the case of k-homology, that by making the operator unbounded, what the bonus that you were getting from making the operator unbounded was that you were now beginning to do really geometry. In other words, you were getting, if you want, a metric from the distance formula. And so, I mean, then you could at least begin to claim that you were really doing geometry, and that because of the framework which had been built in the non-commutative case, if you want, this was really the the natural framework for non-commutative geometry, because it was using space and so on. So that's when I introduced spectral triples, I mean, at the beginning of the 80s. And then, you know, I had students, Page and Jules, and they did their work on the generalization of this unbounded version to the bivariant case, to the Kasparov case. And as you mentioned, I mean, they were mostly motivated by the external product, namely what they discovered. If you want the reason for what, but this you said perfectly. The reason for their unbounded version was that then it made the external product perfectly well defined. Now, in the work with Scandalis, we had noticed that we needed something like a connection. And my general remark is the following. It's clear, if you want, that there is an intimate relation between the idea of connection and geometry. And this, I think, you have quite well explained in the various examples. I mean, it's clear, if you want, that I don't remember if it's Élie Cartan, or I don't remember whom said that to solve a geometric problem, you have to find the correct connection.
Yeah.
So I mean, and this is really the name of the game in this story. Okay, on the other hand, if you want, if one wants to view things at the conceptual level, one has to be very, very careful, because if you present things by saying that the ultimate goal is to get KK classes and to get composition, that's not a real justification. I mean, it doesn't, if you want it, it doesn't sort of display the depth of the geometric side. You see, so what I mean is that, okay, it's true that one can do a lot of computations using the unbounded version and so on. But I think what one is doing is something which is more precise and which is approaching the category which is underlying geometry. Let me try to be more precise. You see, when you are doing Riemannian geometry, the objects are very well defined. They are Riemannian spaces, they are Riemannian geometries, and nobody can question that this is the right one for ordinary classical physics. However, if you ask Riemannian geometers, do you have a category? In general, you know, they would be unable to give you a nice answer.
Sure.
Because they have the objects, but if you ask them what are the morphisms, well, okay, they will be in trouble because precisely of this issue that we are dealing with. If you want, in the sense that it is clear that when we represent geometric spaces, say by spectral triples, and we try to represent morphisms by unbounded KK classes, we cannot really have a category on the nose, because having a category on the nose would prevent you from the choice of a connection, which is exactly the point.
Yeah.
So you see, so then this means that if you oversimplify and you say, oh, but I am only interested in the KK class, well, in fact, you are not doing the right thing, because you are reducing the fine structure that you have, that of a correspondence, really. Because I mean, these things that are behind the scene are, as you showed in the last example, they are geometric correspondences.
Sure.
And so, I mean, you know, I think one should insist on the fact that it's not really KK which is at stake here. It's really geometric correspondences.
No, exactly. Well, we are trying to carry the geometry around, but it's important not to lose contact with KK as we go.
Exactly. Yeah, you see, of course, KK is a kind of safety net.
Yep.
Because I mean, you shouldn't compute something which is not the cup product, of course. I mean, you should compute the cup product. But you should have in the cup product a representative which is meaningful geometrically.
Yes.
And this goes very far. I mean, you know, this is at the heart of non-commutative geometry, clearly. I mean, you know, but it has to be stated correctly. It has to be stated correctly. I mean, that's why, you know, for instance, I much prefer the name spectral triple than Kasparov module. I mean, I introduced the terminology of unbounded Kasparov module in my book,
sure.
but one should be able to refine the notion and really drop the homotopy equivalence and try to see what one gets. I don't know if it's a category, if it's a derived category. I don't know exactly where it fits in the categorical language, but it certainly fits somewhere. You see, might be a derived category or something like that. I don't know. I have no, this I cannot say. I cannot be precise there.
I have no answer for that one today.
Yeah.
Thank you.
Maybe I comment briefly.
Yep.
On the things Alain said also. That this, Alain, what you're describing is for a long time now has been my motivation for studying this whole structure.
Thank you, Bram. I didn't want to say it for you.
Yeah, very good, Bram. Yes.
Exactly this refinement that you're talking about.
Right.
So to put a finer structure on the unbounded cycles such that you get a category
the geometric meaning, exactly.
thereof is exactly the goal, but the technical details are quite involved because what the hard thing to show is you can impose conditions on the cycles and compose them, but then you need to show that the composition satisfies the same smoothness criteria again.
Exactly.
And I have it's something I've been working on for years now, and I'm making steady progress, but it's not completely finished yet.
Yeah, I think it's a central topic, really. I mean, but it should be improved and sort of in the right way also, and presented in papers in the right way. Because if one insists on the KK class, well, this is not really convincing. I mean, one really
no, this is not the goal. This is, as you said, this is a sanity check.
Yeah.
The KK class.
Yeah,
that's what you need.
Of course, it's a safety net.
Yeah.
Exactly. Of course, that's what you need to preserve. Exactly. Sure.
Can I add a comment on this part?
Sure.
As it turns out, in the geometric setup of spectral triple, if you go back to more classical geometry, you also include the case of fractal spaces.
Oh, yeah.
You don't necessarily include automatically Adam, because you've been working on that, but you don't include necessarily a manifold. And it's actually very interesting because there is a chance that we could define a category of compact metric space, to make things simple, for which the existence of an operator like the Laplacian, the Laplace-Beltrami operator, is possible. There are many people working on that with various approaches, but the non-commutative geometry approach is extremely inspiring.
I think it would be fascinating if you had a category of compact metric spaces, as you say, to try and build a version of the Hutchinson operator in that context, to build the limits of iterated function systems and use Gromov-Hausdorff convergence. I think that would be fascinating.
Yeah, there is in fact another example which Jean reminded me of, which is the example of supersymmetric quantum field theory. When you take supersymmetric quantum field theory, you do have a spectral triple. I mean, it's no longer finitely summable.
Yeah.
But so I mean, this, if you want, this geometric formalism is suitable for a lot of different examples. I mean, fractals and infinite dimensional geometry. I mean, otherwise you couldn't define what it means in infinite dimensional geometry like quantum field theory.
Certainly, all of the spectral triples we build for Kunz-Pimsner and Kunz-Krieger algebras.
Yeah, exactly. Exactly. I mean, it's the same. Exactly the same type. Exactly.
Yeah.
Anyway, thanks a lot for your talk.
No worries. Thank you.
Can I ask you a quick question, Adam?
Oh, yes. Hello, Jono.
Hey, Adam. How you going? I wanted to ask, so there's a lot of this talking about connections, and this is possibly more just coincidental than anything, but in Blackadar's book on KK, there's mentioned these F connections to function in the place of this one tensor K or one tensor T operator.
Yeah, this is the version that Elaine was referring to. It's sort of the bounded version of a connection for.
Yeah, this is
Okay.
Yeah.
If I can share my screen, I can even show you.
Sure. I will stop sharing.
Can I share my screen? Yeah, I can show you the place. I mean, you see, so this is the appendix to our paper with George Skandalis.
Yeah.
And then we define connections as for the bounded case. For the bounded case. So this means that whatever you do, you will never have a uniquely defined. I mean,
no.
Except you will always have to choose a connection.
Yeah.
And as I said, you know, this fact that you have to choose a connection is a subtlety which has to be understood. It is similar in algebraic geometry. I mean, in algebraic geometry, the correct notion of morphism from a space to another is that of a correspondence. And when you want to compose correspondence, you have to make them transversal. So I mean, it is something which is built in. But which one has to understand at a deeper level, you know, really. But which one has to emphasize? I think the important thing is to understand that this geometric aspect should be emphasized. I mean, it should be really, really, and as Bram Mesland was saying, I mean, it should be also distilled. It's not yet distilled. I mean, one doesn't yet exactly know what one is doing. You know, what are the objects? What is the category and such things.
Yeah.
Cool.
So
Thanks very much.
I think Elaine's connection roughly corresponds to the one tensor nabla D that I had, and take the bounded transform of that. That's
exactly. This is the same. Yes, yeah.
Okay. Cool. Great.
Are there other questions or comments? All right, in that case, let's thank Adam for a wonderful talk. And next week, Wilhelm Winter is going to give a talk. So thank you very much, everyone. See you next week.
Thanks you all for coming along. See ya.
Thanks.
Thanks. Bye.